Yeah, let's go ahead and get started. We're going to be talking about supply chain security, some of the stuff that's going to Drupal's automatic update system, and some of how packagist.org works, and a overview of what supply chain security is. I'm Nils Adermann. I'm the senior technologist at the Drupal Association. I've been doing some of the kind of helping pull everything together on the server side of Drupal's automatic updates. We also have Christopher Gervais and Nils Adermann. Yeah.
Yeah, welcome. So I created the Composer project that hopefully you're all kind of familiar with, have heard of, have used a lot, depending on your background. And since Drupal is built on top of that, or using it, a part of supply chain security for Drupal, of course, involves Composer. And I want to start with just making sure that we're all kind of on the same page, depending on what background you have, and just talk about what is a software supply chain, because that's the thing I've had conversations about at this event, and that's not necessarily clear to everybody. Because I mean, we've all heard of like actual supply chains, like problems with these over the last couple of years have been in the news. So like that's like a subject that I think everybody's come across at this point. Issues with shipping things, like packages, not like problems getting things to places. But we're talking about software supply chains, and that's a bit different from logistics and like actual physical products. If you look this up on the Wikipedia, you'll find the following definition. A software supply chain is composed of the components, libraries, tools, and processes used to develop, build, and publish a software artifact. Now, all right, that's a lot of words. In other words, you can kind of think about it as the full stack. You know, the thing that you see in like job ads sometimes. Like all the processes and tools involved in making and assembling that stack, all the tools that are in there, all the dependencies, all the packages. If you look at this, like if you're thinking of something like Drupal PHP application, you've got like frameworks, libraries in there, and then those use tools like Composer, PHP unit. They run on top of PHP. PHP itself like sits aside like a web server or a database, like other types of tools that are part of your stack. Then internally, it's built on C libraries like libc, like libxml or OpenSSL, which in turn are all built with the C or C++ compiler, and like they're being produced somehow and made a part of this. And they sit on top of like some operating system which contains a kernel. And I mean, this is a huge oversimplification, right? I'm like, this is already a lot of things, but there's so many other parts in between here that I'm skipping over. And then this all runs on some hardware. And even the hardware is like so many layers if you actually look at modern hardware. It's always a bit funny, this whole job ad thing. Like, what are we talking about with the full stack? You certainly don't mean this thing, because I don't think there's anybody around who like really gets this from the top to the bottom in detail. Like, you know, good luck finding that person who understands modern CPU architecture as well as building a Drupal application. And then you take this a step further, right? You flip this on its head and you go to the other side, because we're talking on the web, so you got this on the client again, right? You've got some JavaScript libraries and frameworks, and that thing runs in a web browser, that web browser runs in an operating system on hard. Like the stack just keeps getting bigger, right? There's so many things in there, and it's impossible for any one individual to fully grasp and understand all of these components. And we're talking about supply chain security, right? That's your supply chain. It's gigantic. Nobody understands all of it. It's hard to manage. And as a consequence, that's a thing that can be attacked. Not just your application, the code that you're writing in your Drupal application, but like all these other bits and pieces that are a part of running your Drupal application. And here's a few famous examples, just to give you an idea of what we're talking about in terms of supply chain attacks. Heartbleed was an issue 10 years ago now. That allowed people through the web to access internal memory of web servers. You could just send a request and you'd get back internal keys, passwords, things that were stored in memory on the server. Catastrophic. There was a thing in 2020 where an automatic update process, an update process was taken over through a built system at SolarWinds. And this was used undetected for several months, or I think over a year, in various US government offices, in like lots of governments across the world too. I think the US was particularly targeted in this particular instance. And that really shows just, yeah, like how common or like how bad the impact of something like that can be, where the software itself looks fine, like you're buying it from a vendor that's actually doing a lot to do work on security, but like somewhere down the line, there's a thing that somebody manages to break into, and then all the next steps fall. Log4Shell was a thing that hopefully a lot of people heard about. It was a vulnerability in a standard logging library for Java that's kind of in everything everywhere. It's kind of impressive in how many places this thing was used. And it was there, like the vulnerability existed for 8 years without anybody noticing. It allowed arbitrary code execution on any system that was running this and exposed to the internet. It took forever. I think there's probably still lots of places out there running a vulnerable version of this library today. Because this is just so deeply like the dependency of a dependency of a dependency of something somebody's running somewhere. A more recent and very fascinating story, I'm not going to be able to go into too much detail on these things, was a library called liblsma and xed utils. Probably nobody ever heard about this unless they read about this particular story. This is a compression thing that ends up being bundled with SSH or OpenSSH on a bunch of Linux distributions. And as a consequence, somebody who socially engineered himself to take over maintenance of this library ended up building a backdoor into SSH that got detected through pure coincidence briefly before this got rolled out onto major Linux distributions around the world. Again, fascinating story. If you're interested in this kind of stuff, read about it, like all the details that people later figured out about what was going on there. But yeah, fascinating. That's one of these things is like, because if you're attacking a supply chain, it's never a direct, like this is the security issue, that's what I'm attacking, where there's always like so many steps involved, and somebody who really figures this out is fascinating. But we want to talk about Composer and Packagist. Now there's things that actually happen in our PHP ecosystem in this direction. Fortunately, nothing so far really led to anything too major. These are some examples of supply chain vulnerabilities in Composer. So there are, a security issue for any Drupal project using Composer. There were cases here where on specific file systems, somebody could run code if you made them check out clone a particular Git repository through Composer. Like usually these scenarios were pretty unlikely, so luckily, as far as we know, never got exploited before somebody reported them. There were cases where code could be injected through URLs in the repository definitions in Composer. That's the bottom two ones. There were people actually trying to attack, like this was just vulnerabilities discovered by security researchers, people actually trying to attack the system. There's a thing called GitHub repo jacking, where if you decide to move your repository on GitHub to a new name in a different place, then the old name keeps redirecting there. But eventually, if somebody else registers a new repository under this name, it replaces that. And if you have references to the old URL somewhere, suddenly you're installing that thing that somebody else put there now. And that's repo jacking, so somebody takes over a GitHub repository, so to speak. There are now mechanisms in place to prevent this, so you actually identify the specific identifier for this repository so that you can avoid this situation in Composer. It's still something to be aware of. Somebody managed to take over some old outdated accounts on packages.org that had poor passwords, didn't have two-factor authentication enabled, and through that managed to modify Doctrine, popular database abstraction layer, to point to a different URL for downloads. Again, luckily, somebody who was just advertising that he's a security researcher and he'd like to find a job in a README that he added. But it still shows there's a real danger there of something happening, of somebody exploiting this for very bad and malicious intentions. Now, to understand a bit better how these things impact Composer, this is a graph I feel like I use in pretty much any presentation I ever do about anything related to Composer, because it's just so important that people who work with Composer understand this. There's commands like Composer require or remove that people interact with that are just shortcuts to editing the Composer JSON file and running a Composer update. The key distinction between Composer update on the left and Composer install on the right is that Composer update generates a log file based on the JSON definition and metadata it receives on the internet. And then Composer install reads the log file, downloads the actual code, and puts it into the vendor directory. Composer update, for convenience purposes, runs a composer install automatically right afterwards. So when you run a composer update, you do end up with files in your vendor directory. That's not because composer update is responsible for doing that. It's just because it triggers the install right after the update. And I think it's important that people think about these two processes as such separate steps. And it also means that the install on the right, you see it doesn't actually contact packages.org. It doesn't get any of the metadata because it's just reading the log file. And that's where all the metadata is at that point. Versus the update, which doesn't touch any of the code, right? It's just dealing with metadata. And that's really a key takeaway. Packages.org doesn't host any code. So if you're not using a Drupal repository for a Drupal module, so you're just installing some regular PHP packages off of packages.org, those come from whatever URL the maintainer decided to host them at. So 99% of cases, that's somewhere in GitHub, but it can be any random website wherever they decided to point the URL at. It's important to understand that there are no checksums because the code that's being installed from GitHub is like the zip files generated dynamically and they change. There are no signatures from maintainers on this code. So the trust in that process relies entirely on everything running through TLS and having to trust packages.org, having to trust GitHub to not modify this stuff and not having been taken over. On a positive side, this means nobody can upload code to packages.org, so we sidestep a whole set of issues that other package managers have where you kind of need to deal with the authenticity of this artifact. We just don't have any. And so the question is just down to, do you trust that the zip file that GitHub generates matches the source code that they also host in most cases? It does give you a very direct link between the actual source code that people are posting publicly and the zip file that you're installing from, because they're generated directly from the place that also hosts the source code and the version control system. It's a bit of an, I think, upside of this. And it means that there's a smaller attack surface on packages.org too, because really in the end, it's just a list of URLs, right? Like that's kind of all it comes down to. But I think it's important to understand that that's how this works. Composer has a command that's relatively recent, Composer Audit, which works great with Drupal packages too these days. And that checks your dependencies that are in your, like that you've currently got installed against public vulnerability databases and informs you if there's any known vulnerabilities published against any of the versions that you're currently using. So that's a thing you should include in your CI runs, or maybe just have a thing that automatically checks that. Or there's lots of tools out there that help you automate checking for this and notify you when there's something. Like I work on one, Private Packages, which is our company that we use to finance working on the open source project Composer. It's at packages.com, just like packages.org for the open source packages. But there's lots of other tools that do similar things. One thing I do want to get at, because people keep suggesting to me that, oh, can we fix these problems by vendoring? And for those who don't know what that is, it's the idea that you can just commit all your dependencies into your repository, right? Composer typically generates this vendor directory, and then why don't I just commit all these things and then I don't have to worry about anything? Now that doesn't really solve any of these issues. Like even if you do that, like it does mean that you don't have to install them on deploy, but you still have to update these dependencies. So either you're still relying on the package manager, so you haven't sidestepped using the package manager, or now you're going to like manually downloading all these individual packages and like making sure that they're updated. And that's such an error-prone process. I think anybody working with Composer should be kind of happy to have left that time behind. But there are other problems with this. Like it's super easy to miss removing files. Like I've seen people do this and they're like, great, I can like add the vendor directory after I do an update. And then they keep doing that. And eventually they realize, damn, like this one file that got deleted in my dependency that contained a security vulnerability still exists in my repository, because they totally forgot if you just do git add, that doesn't remove any files that got removed in your file system. You got to like add other flags for that. And then you're relying on every developer in your team that does these updates on knowing that that's how this works, or building your own automation to do that, which again is like a lot of extra work. It actually is way more complicated to manage conflicts in that setup than it is to just manage conflicts in the log file. Like, I mean, yes, those are annoying and you have to deal with them, but compared to having the whole tree of files to manage conflicts with, that's something. And it gets worse if you have like some actual bad actor, like some employee who's just got fired and he wants to like leave something behind, or like he knows that's gonna happen, and then he sends a giant pull request with all the changes to your dependencies, and somewhere in there he just adds a couple of files that nobody notices and that aren't being tracked by Composer. Good luck noticing that in a review process. So instead, like our typical recommendation from Composer's perspective is run your own Composer repository. So use a tool like Private Packages, Artifactory, Nexus Repository, Gem Fury, there's like a bunch of these, to make sure that you have your own artifacts. If you have a copy of all these dependencies that you have stored, instead of relying on them being on some random website on the internet, which is what happens when you just use packages.org, like rather add that extra layer in between so that you have something that you rely on that is under your own control, so that things that go away you still have a copy of, for example. Or that if somebody on an open source project decides to change a git tag to point to some other code because they quickly wanted to put a fix in, you actually notice that and you see that the code you're currently deploying doesn't match what you originally installed. Again, a thing that happens, but if you have your own repository, you can control this. Now I put Drupal on here because the situation is a bit different if you're using packages.drupal.org for Drupal modules, and I think that's what we're getting at now, because Drupal actually does host the files, and so you have different security guarantees around that, and those we're trying to improve even further. So that's up next.
I'll get into a brief summary of the automatic updates for Drupal initiative. So the overall aim is to automate using Composer and provide a UI to that. So the components range all the way from the server side to the client side. So on the server, there's packages.drupal.org. That's getting some improvements. And a rugged tough server, that's the update framework, which we'll get into in a bit. And that provides the signing capability on top of the zip files that we already host that Composer downloads. And then going more towards the client side, a PHP Tough integration plugin for Composer, which tells Composer how to verify those signatures from the update framework specification. And then providing a nice UI for that. Package Manager is kind of more behind the scenes. It's the support module for automatic updates and Project Browser, which are more UI focused and get into things like deciding when to install an update, managing attended updates. Most of the time we'll be going to the admin UI and clicking update. It's more the fully automatic is for security updates. And yeah, the overall idea is we're scaling the last mile of the process. The more protecting you from if someone's able to take over Drupal.org or impersonate Drupal.org in that range. So I'll go through a very brief overview of how Drupal.org projects are packaged. So you create a release on Drupal.org that goes into a queue, and it creates the zip and chargez files for download, and updates the packages.drupal.org metadata. And then what we're adding is sending that both the zip file that was packaged and the Composer metadata to Rugged to be signed. They'll both be signed, so everything can be verified. And then Rugged will update that signing metadata. Drupal core is a little different. We want people to be able to compose or create project Drupal core recommended without knowing about packages.drupal.org first. So that goes to GitHub, and the core components are there as well. And packages.org will keep doing what it's doing, but we're adding a mirror of that, which will make a copy of the zip files from GitHub, so it won't be possible for if GitHub changes how they package their zip files, or if something else happens to ruin the integrity of those, we'll have a static copy. And again, all of the metadata and the zip files are assigned. And then a newer type of project on Drupal.org is general projects. As we're moving towards more of a composer native workflow, it's modules and themes have some workarounds that packages.drupal.org exists for. When we're adding new things like recipes, we don't want any workarounds. So those are using Packagist and Composer as intended for any other PHP project. So those are, we host all that code. The zip files get downloaded from git.drupalcode.org, but we're using packagist.org for the metadata and not our own packages.drupal.org. And then the rest is the same as it was for the Drupal core. So the actual verification is tough.
All right, that was all really straightforward. And this is where things get a little complicated. I'm going to explain public key cryptography, digital signatures, and how hash functions work. And I'm going to take about 4 minutes to do it. So bear with me. I'm really going to keep it as basic as possible, but just so that you understand the principles behind it, so that you understand what Tough is doing and how it helps to secure any of this stuff. So this is often helpful to look at it as a real-world example, right? So the idea here is, the fundamental idea is asymmetry. So things that are sort of go one way. A good example of this is if you want to send me a letter, all you need is my address. You don't need to know anything else about it, about me, how I get access to my mailbox or anything like that. For me to then access that message, I need the key to my mailbox, right? So my key doesn't help me send you a message. And if you had a copy of that key, that wouldn't help you send that message to me either. Okay, so that's the fundamental idea of what asymmetry is about. And note that we have this public and private concept, right? The key is private in that I have it in my possession, and I'm not going to share it with anybody else. My address can be published anywhere, and that's fine, and it doesn't harm my security for people to know where to send mail to me. So where this starts to get a little more complicated is when we start looking at the math behind key pairs. Okay, so we're not going to look at the math behind key pairs because I don't understand it, so I'm not even going to try to explain it. But basically what we're doing is using very large random numbers to generate two files. Okay, those files have what look like random digits and numbers and letters in them. But these two files have a very particular relationship with one another, which is that if you encrypt something with one of them, the only thing that will allow you to decrypt it is the other file. So these keys are two files, but they're paired together in that fashion. Now, another important element to think about here is that you can actually reverse this process in the fact that it doesn't matter which key you encrypt something with, only the other key will do it. But you can use either key in that fashion. By convention, we set one of those keys to be private so that you know to keep it safe. And then the other one is designated as public and you publish it, okay? So, yeah, let's keep it at that for now. So the way this works in sort of the usual sense would be if you want to send a private or a secret message, you would use the my public key that you would be able to find on the internet somewhere, or possibly printed on my business card or something along those lines. And you would be able to use that key to encrypt the message. And when you send that message to me, even if other people intercept it, like say email servers that are not in your control, you can be sure that nobody else is going to be able to read that message because only my private key that I am being very responsible about keeping private will allow anybody to decrypt it. And so since I'm the only one with that, I'm the only one that will be able to read that message, okay? Now, this is only relevant if the message is secret. But remember that this works kind of both ways. So what we can do is instead, if you want to make sure that the message came from me, instead of caring about whether it's secret when you send it to me, you can take that, I can take the private key when I'm sending a message, And I can encrypt the message and then send it to you, right? And then you can look up my public key and decrypt the message, and then you'll know that that message hasn't been hacked, right? It hasn't been altered in any way. So that's essentially what this works, the way this works. Now, in this case, the message isn't secret. You can wrap these things together to make secret messages that are also signed, but that's not really relevant to the specifics of what we're talking about here. The last thing we have to understand is how hash functions work. Basically, it takes some set of input and it kind of scrambles it into a defined length string, okay? And essentially, you can't go backwards. It's a one-way function, okay? However, essentially, every time you put a different input in, no matter how small the change, you're going to get a completely different output as your hash sum, okay? Now, that's technically a lie because it's a smaller set of data, and so there's like actually an infinite number of things that can generate the same thing, but practically speaking, it's impossible, okay? So what this does is it can prove that a file hasn't been altered. So if you're sending something to me and you publish that hash, you've probably seen this with like ISOs for Ubuntu or something like that, right? There'll be a hash next to it. When you download that file, the reason for that is partially security and partially just integrity, right? You want to make sure that there hasn't been a bit swapped somewhere along the line and you end up with a corrupted ISO. So that's basically what this is doing. It's just proving that the thing hasn't been altered. So now we have all the things we need to understand how Tough works and helps with this, okay? So this is basically going over what Neil already mentioned. So the packaging pipeline generates a zip file and hands that over to the Tough server. The Tough server takes a hash of that file and then signs that with its private keys, okay? That then gets published as the Tough metadata. Now, we'll look at a little bit more what that looks like in a minute. But then when Composer goes to download that file, the plugin, the PHP Tough Composer plugin, will download the Tough metadata and be able to check the signature that was generated against the hash that it can take of the file locally, right? And with that, it can make sure that the file that was downloaded has not been altered in any way. So I'm going to go a little bit more into where the Tough framework came from and what it's about. Okay, so the Tough framework, which is the update framework rather, which is what Tough is comes out of academia. So there was an analysis done over decades, basically, of different types of attacks on updates and other things. But updates in particular were a vector that they were getting really concerned about, because bear in mind the impact of hacking a module on Drupal.org or being able to do something like that is that everybody that's got that installed, all of those sites are now vulnerable, right? As opposed to hacking one individual site. So it has a much broader impact than a directed attack. So they were doing this analysis, and they came up with, I think, 22 different types of supply chain attack. And it ranges from man-in-the-middle attacks to freeze attacks, where it's trying to serve you older versions of the same module, even if it's, it's the same code that used to run, but there's a bug in it that now they know how to exploit, for example. And so they came up with these principles of what this framework would try to accomplish in order to secure updates. And basically, it comes down to these 5 things. So when they're talking about trust, this is sort of a computer science element of trust. It's not how we normally think of trust between people. But a large part of it comes down to narrowing the scope that you have to trust any particular data to a particular, so for a particular type of data, you need to trust that somebody with a private key signed it, right? But narrowing that as much as possible so that if somebody were to compromise one key, it doesn't mean they've got access to change everything, okay? So that's where the compromise resilience comes in. So using multiple keys and minimizing the trust placed in any individual key, and we'll see what the keys look like and how they divide this up. Then you get into the sort of more practical matters of integrity, so what we just described about verifying that the package hasn't been changed. And then freshness. So again, that freeze attack element of knowing that you're getting the latest version and that you're not being tricked into thinking there hasn't been an update. And then implementation safety, that Tough itself as a component of this workflow now doesn't introduce any new problems. So the way that Tough does this is we publish a bunch of metadata. Now metadata is just JSON. We'll see an example in a minute. And there's sort of four like elementary parts to this. There's a whole bunch of other stuff that can come into it, but these are the basics of what's needed to make this work. And so the first one that we deal with is root metadata, which just defines what keys are allowed to sign what other metadata throughout the rest of the repository. This deals with trust and compromise resilience, right? So on the right here, you'll see what it is that these types of metadata are trying to secure, right? What they're trying to accomplish. Then we have timestamp metadata. So this gets refreshed every 5 minutes or so. So that's how you can know if somebody's trying to trick you into thinking that something hasn't been updated. Then there's snapshot metadata, which makes sure that all the metadata itself is secure, that somebody's not trying to tell you that, no, this is really trustworthy, don't worry about it, right? So the Tough metadata itself is all secured by the snapshot metadata. And then finally you get the targets metadata, which is the one that has the list of all of the packages and all of the versions of those packages and the hashes of all those packages, et cetera. That then has the ability to delegate to other roles that can do a bunch of things, mostly for performance and scalability. So I'm not going to cover them here. So this is what Tough metadata actually looks like. This is an example of a targets file. And it's JSON. We should all be reasonably familiar with that. What you'll see is there's two top-level items. There's signatures and signed. Signed is the part that the signature is signing, right? So up there, you've got a key ID, so it tells you what key is being used to sign it, and then what the signature is. That's what allows any of the rest of this, and in particular the Composer plugin, to verify that this metadata is correct. Then you've got the signed portion. In this case, it's the targets metadata for a file that's called text1.txt. Test1.txt. So that would normally be something like, views.zip or something like that, right? Then it has the hash. It happens to be a 256 hash and the length of the file itself. And these are the things that that local Composer plugin can verify that all of these downloaded files exist. And then we've got the other ones that I just explained, right? And what exactly it is that's in each of them. But essentially, it looks just like this. A little bit longer, some of the keys have changed. That's it. So the Tough server, the rugged Tough server in particular, is one that I've been building on behalf of the Drupal Association for the past couple of years to generate all this Tough metadata to secure all the downloads of all the modules and themes and so forth. And basically, it's relatively straightforward implementation of the Tough framework with an added twist of trying to keep all of the keys that are responsible for signing the various metadata completely isolated from one another, which just adds an extra layer of difficulty for anybody trying to compromise this. It aims to make things simple and robust. We'll see how it makes it simple from the Drupal.org sort of packaging pipeline standpoint. Robust insofar as the packaging pipeline doesn't actually have any keys. It doesn't have any access to anything with rugged. It just kind of puts a file in a directory that's on a shared file system, and that's it. This was all sponsored by the Drupal Association, and back in January, the OSTIF, which is the Open Source Technology Improvement Fund, sponsored a security audit, and there were no vulnerabilities found, so that was nice. There were some very minor things with regards to like development environments, but anyway, clean that up. Just quickly, the components, there's a CLI component, but most of it is actually working within these daemons. So there's a targets worker. Its main responsibility is just to sign targets metadata. So it'll look at the file, it'll take the hash, it'll write it into the targets file, and then it will write that back into that shared file system, right? Then the snapshot worker will come along, and for every update to the targets metadata, it will pull that together into the snapshot metadata, sign that, publish it to the shared file system. Then the timestamp worker does the same thing for the timestamp metadata. There's a monitor worker involved here as well. That's what scans for new uploads. So whenever the packaging pipeline puts a file into that shared file system, that's the thing that notices and goes, oh, there's something to do, and then tells the rest of the system to start processing that stuff. Also, one of the things that I kind of skipped over a little bit is that in that metadata, there's an expiry timestamp. So remember that the trust element is partly a matter of compartmentalizing which keys are valid for which data that you're publishing, but also that it's only valid for a certain period of time. And so every once in a while, the monitor worker will wake up, scan the metadata, make sure that everything is within its expiry date, leave things alone. Or if it finds that something's about to expire, it'll just update that, re-sign whatever needs to be re-signed, and proceed. There's also a root worker, which is not meant to be running on a regular basis, and it does some utility functions like initializing repositories, generating keys, and so forth. So this is a sequence diagram. Time is going from top to bottom, and these are just the workers, the elements that work within this system. Okay, I'm going to go through this quickly. It's the same diagram as on the left there, but legible. Okay, so I just had to break it up a bit. You'll see that each of the workers has a key. The pipeline does not. It does the basics of cloning the project, building the package. It uploads the package. It generates the package metadata, which is the composer files. Uploads that into the shared file system. Then the monitor worker is in that loop scanning for new targets that I just described. Once it says it notices one, it triggers the targets worker to start its job, reads the targets file, generates the stuff, writes it back into the file system. The snapshot one does the same thing, except there's nothing to read except the targets file, which is the one that it's signing. And then finally, you have the timestamp one that does the same thing. Except for the timestamp, it's the timestamp metadata signed by the timestamp key. So then the final kind of step here is the client-side component of this. So there's two main pieces. There's a PHP Tough library, which is just a tough implementation in PHP. And it's focused on PHP CMSs. So a lot of the work was done by people at Acquia, but it was also supported by the Drupal Association and folks at Typo3 and Joomla. It was also part of that same security audit in January, and no significant vulnerabilities were found. There was like some minor stuff around paths on the file system, but that was quickly cleaned up as well. So then that library is used by the Composer plugin, which basically hooks into Composer. Every time it tries to download a file, it says, okay, do I have metadata about this file? If so, let me download the appropriate targets component for it and run the hashes and check that everything is correct. Note that all of that takes some time. It's downloading some more files, and it's running some hashes, and it's doing some stuff like that. So it does slow down Composer a little bit, but that shouldn't be that big a deal. We're not running that kind of stuff all the time. At the end of the day, this is what allows auto updates to basically check for those hashes so that when it's running, you can be sure that everything it's getting is coming from a trusted source. And it was also part of that security audit, and again, passed with flying colors. So that's it. There's, I think, one more slide.
Yeah, so all of this is, on the server side, it's pretty much in production. There's some loose ends we're cleaning up as far as like making it even more productionized and easier to maintain. But the main thing it needs is testing from the client side. So yeah, everything's been security reviewed, and we've dealt with any of the minor findings. And use the automatic updates project to test, get a preview of what it will look like. And right now, the next step for Drupal core is getting the package manager component into core itself. So there's an issue for that. And the auto updates channel on Drupal Slack. And then, I'll be around Sprint tomorrow. I believe.
In the morning, at least, yeah.
Yeah, we'll be around tomorrow. And I think the only thing that's left is general contributions are tomorrow. Please come and work on this or anything else. And yeah, there's a survey. Any questions? I don't think I've seen any on the app, but yeah, please step up to the mic.
Hi, thank you for the talk. I have a bunch of questions, and if I overstay my welcome, just let me know. So does the Composer plugin is embedded with a public key to check the overall keys, or?
So it's, yeah, there's going to be a way to, oh, yeah. So yeah, it'll have the root metadata, actually. The first root metadata is what it's going to come either packaged with or have some secure method of getting it to you.
Was that the payload that we saw in the JSON at the beginning? No.
It's similar to that, except what's being signed is the list of keys that are valid and what roles each key is valid for signing. So I can show you afterwards if you like an example of what that looks like, but essentially, yeah, it's just a list of keys and a list of roles and which key is valid for which role.
Okay.
And so that includes the public key for each one. So that's how you get those locally.
And why is there a need for a shared file system?
That's just the mechanism we're using for communicating this stuff. What we wanted to do was make it so that the packaging pipeline didn't require any keys or special access to any of the system. Okay. So this keeps it very isolated from one another.
So it's basically a way to share data for the CI pipeline, basically.
Well, yeah, from the CI pipeline to the TUF pipeline, which then also uses it. It also uses the shared file system for like some file system semaphores and stuff to keep the processes.
So it's not like a trust issue. Does not create trust issues.
This is also under dilemma.
Under what?
Yeah, so the way we've deployed this is each worker daemon is a separate container. So they need access to the same set of files, the TUF repository. And practically that's a EBS volume on AWS. So the containers can all see the same thing. And then on the front end, how everything gets there in the first place is one of the containers exists solely to be a SFTP server. So Drupal's packaging pipeline, Drupal.org's packaging pipeline uploads the zip files over SFTP to get them there because they're isolated. There's a kind of firewall there to protect that section of the infrastructure from the other section of the infrastructure. So.
And another last question: are you guys thinking about using this like a playground for generalizing it for Composer as well, or maybe expanding for the whole ecosystem, not just CMS?
Yeah, so I think that's from the Composer side. That's kind of what we've been saying here is like, hey, go ahead and build this as a plugin, so we can kind of see like that this works, like makes sense. If you wanted to expand this to Composer, there's like different scalability issues that we don't have on like the Drupal level yet. There's some to be answered there too, but so I think to take this even further, there's additional things that need to be answered, things that the TUF spec doesn't currently contain or allow necessarily, and so there's a few things that to do that eventually we still need to work out. So there's nothing guaranteed at this point. We're definitely looking at that and kind of waiting to see how successful this ends up being for Drupal.
Okay, thank you.
Yeah. The reference implementation of TUF is written in Python. It's for the securing the Python packaging, PyPy, I think, and they actually haven't deployed it yet. So we're figuring out some of the translations from academia to running a system that's in production. Yep.
Just out of curiosity, how does this freshness protection work? Like if you have a man-in-the-middle attack, how does the client know that there is a newer release?
So you're going to have a cached version of all of this metadata locally, right? And so generally what the plugin is going to do is going to check its local cache, and it's going to look at the timestamp one in particular, right? And it's going to see if it's expired. And if it hasn't expired, then it's not going to try to go download anything else. It's just going to assume that what it has locally is still valid. As soon as it expires, it's going to request a new version of it. If it doesn't get a new version, the one that it has is invalid, and it stops, right?
I see.
So it's not going to necessarily work around an attack, right? It's going to alert you that there's an attack, and then you can kind of go from there.
How long is that expiry window?
I think for timestamp it's 5 minutes, but it's policy based. You can set it on the rugged server to different levels.
Thank you.
Sure.
All right, we're technically at time. The closing ceremony is in 15 minutes. So yeah, we'll be around for a few minutes. If there's any quick questions, we can get those. Otherwise, please go to the closing ceremony. And there's trivia later if you're interested in that.
Thank you.
Yep.
Indeed.
Yes, and then sprint tomorrow.